Natural physics is a concept astrophysicist Leroy Larry developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as Leroy's astrophysics doctoral research at CNESPA, Center for Space Research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings. I'm Leroy Larry, and welcome to Natural Physics, live from Costa Rica. I am very excited to say that I received requests to hear more of the questions and answers that occurred at the conclusion of the workshop in Nigeria that I spoke about last week. And I played a couple of the questions at the end of the presentation that I showed last week. And it's just so cool that I had requests to hear more. So I will play that video. Before I do so, I wanted to say that subsequent to that workshop in Nigeria, representative schools requested and received follow-up guidance and assistance, and have since incorporated astronomy into their academic curriculums or as an enrichment program. Oh, I mean, that's the power of outreach. And actually, I'm wearing what I'm wearing for this show was a gift from the organizers of the workshop. And I'll tell you more about it at the conclusion of the video, but basically its colors and its design represent a particular tribal area in southern Nigeria. I mean, how cool is that? I mean, it's as if you're walking down the street in Nigeria and people can look at what you're wearing and tell what tribe you're from or what area you're representing. So we will now get to the video. And again, remember that I think my methodology of communicating as I did to the teachers, to the primary and secondary school teachers in Nigeria, I think they will serve well to do the same with the Borucas. And the questions and answers that you're about to see, I mean, how cool to get that. I mean, as an educator, you want questions. You want questions. I was actually horrified to hear from some students that I had at the university level here in Costa Rica, and not only here, but in the United States as well, where they had teachers who discouraged questions. How else are we going to grow in our knowledge? You have to ask questions. Why does the grass grow? Why is the sky blue? I can't even imagine what kind of teacher would discourage questions. Oh, that's just unreal. Okay, so again, I was elated when I got all these questions from the teachers. And remember, their knowledge of astronomy, I mean, it increased 100-fold because we gave quizzes before and after the workshop that provided a quantitative assessment. And across the board, their knowledge of astronomy increased. So again, that's the power of outreach. And I would hope to do the same with the Borucas. So enjoy these questions and answers. And at the end, you will see my my clothing here in full regalia. And you know I wanted to use that word. Okay, so let's roll the video. This is a continuation from last week where I played a couple of the first questions. Now we're gonna hear the other ones. Okay, here we go. Enjoy, please.
From the lecture, I deduce that humans have been to the moon. If so, how do they return to Earth? Okay, I think I went over that yesterday, right, with the Apollo mission. Do we have humans who have been lost up there? Fortunately not. Apollo 13 came very close to bringing this statement to realization, but fortunately they did not. So no, we have not had humans lost up there. Unfortunately, you probably know about the two space shuttle tragedies that happened. The first one happened when they were on their way up, and the other one happened when they were on their way down. But nobody has been lost in space so far. Let's see. There's questions about curriculum and that type. Again, contact me. I will get back immediately to you, because I think the space application questions are similar to getting in contact with NASA. So what I want to do in these questions is address the scientific questions, but again, you will have my email address. Are robots capable of generating energies from space and used on Earth? Yes. The type of batteries that Curiosity is running on are very, very beneficial to here on Earth. There's a perfect example of space technology being beneficial to us here on Earth. The science and technology that went into inventing and doing the engineering to produce these batteries to allow the Curiosity and there's another rover on Mars too that got there before Curiosity. It's been up there for 10 years. I forget the name of it, but it's been on Mars since 2003, I think. And they didn't think it would keep going past about 9 months, but it's still going. So again, the types of energy generation that has been invented through physics and then put into practical applications by engineering and technology are very, very, very beneficial to us here on Earth. Because think about it. If there wasn't a need to come up with a way to supply energy to this robot thousands and thousands of kilometers away from us, maybe nobody would have ever developed it for Earth. But because we needed some type of way to keep these robots functioning, that made us develop something for that, which in turn can be used here on Earth. And by the way, there's other robots on other planets. There's some space probes were landed on Venus by the Russians, by the USSR. They didn't, back in I think the 80s, they didn't survive very long because the environment of Venus is very hostile. But yeah, Mars isn't the only place where we've sent space probes to that have actually landed. Okay. What is Pluto considered to be now? Is no longer a planet. I think I talked about that. Yeah, unfortunately, Pluto has been demoted to not a planet. And it's still in our solar system, but it's no longer counted as one of the planets. And by the way, it's recently been discovered that there could be some other planets further out that belong to our solar system that, again, because we don't yet have telescopes powerful enough to detect them, we haven't been able to really see them. But when you do studies of how the planets orbit and the physics of the gravitational reaction that has to go between planets, it leads us to believe that the planets we know of in our solar system aren't the only ones. There has to be some other planets further out in order for us to observe the motion of the planets that we see. And I got to go back to what I talked about yesterday, that 6,000-year-old civilization called the Sumerians. Okay, now I'm going to go a little bit further. Remember I said that they said that Pluto used to be one of the moons of Saturn, one of the most outermost moons of Saturn, and that something happened that pulled Pluto away from Saturn and placed it into its own orbit around the sun. Well, what they said this something was, the Sumerians believed they called it the 12th planet, and they called it Nibiru. They said that another planet, and the reason why it's called the 12th planet is because the Sumerians counted the sun and the moon as part of our solar system. So you got the 9 planets plus the sun plus the moon, which gives you 11. And then according to them, there's this 12th planet that takes 3,600 years to orbit the sun. So one day on Nibiru is 3,600 years on Earth. And they said that every time Nibiru comes around, every 3,600 years, it does something. So one trip through, it passed close by Saturn, and its gravitational field captured Pluto, which was a moon of Saturn, dragged it away from Pluto, and placed it in its own orbit. Now, this may sound pretty far out to you, but think about it. Why would anybody even make up such a story? I mean, I can see 6,000 years ago, some Sumerian sitting there saying, okay, I'm going to say that there's a 12th planet, and I'm going to say that it did this. And then 6,000 years later, people are going to read this, and they're going to believe it. You know, why would you even say something? I mean, you can't even make up something like that, right? So, again, going back to the fact that we've just now started to detect the possibility that there's actually other planets in our solar system that are so far out that we have not yet been able to detect them. Well, who's to say there really is not a planet that comes around every 3,600 years but is a part of our solar system? Remember comets. Comets are a part of our solar system. They do orbit the sun, but they have trajectories. Halley's Comet, every 75 years it comes around. So and they're part of our solar system, comets are. So who's to say that there's not a 12th planet or another planet that takes 3,600 years to do an orbit around the sun? Okay? So, again, there's a lot of mysteries, not only about our solar system, but right here on Earth. There's a lot of mysteries right here. Okay. Let's see. Like I said, I'm going to go through these and pick out the ones that we may not have answered yesterday, and also the ones that are related to astronomy. Okay. Is it possible to bring sand particles from the moon back to Earth? Yes, moon rocks have been brought back. The first moon rock I ever saw was when I was at the Jet Propulsion Lab. And in the administrative office, as soon as you walk in the lobby, they had this really nice glass casing that had a moon rock about this big in it. Looks like a rock from Earth, kind of grayish in color, just like a regular rock. Let's see here. How do you establish a communication link from a faraway place on Mars and Earth ground station? It's by radio waves, okay? And in fact, here's something interesting. You know, a radio wave is a form of light. I mean, remember the electromagnetic spectrum, where the radio waves are the longest wavelength and the least energy? Well, when I was on the Galileo project, when we wanted to send the command, once Galileo got to Jupiter and it established orbit around Jupiter, To send the command to Galileo, it took 45 minutes for that command to get to Galileo. At the distance that Jupiter is from the Earth, it takes light, or it takes a radio signal 45 minutes to get there, okay? Now, Curiosity, which is on Mars, I believe the time it takes is about 20 minutes, something like that. So think about this. As Curiosity is roving around Mars, and say the scientists want it to make a turn and go in a certain direction, they got to send that command 20 minutes before they really want Curiosity to do what they want it to do, because it's going to take 20 minutes for that command to get to Curiosity. And in reverse, when Curiosity is sending information back to us from Mars, it takes 20 minutes for us to get it. Galileo, it took 45 minutes for the data from Galileo to get back to us here on Earth. So the communications link are possible. Radio waves move in a straight line. If there's anything in the way, they can't get through it. If it's big enough, like a plant, like a building, as you saw yesterday. But you got to keep in mind that there's going to be a time delay because of the distances that you're talking about. Okay. Some people want to know about the Bermuda Triangle. What is the link between the black hole and the famous Bermuda Triangle, where aircraft and ships disappear? This has definitely occurred. Now, a strong magnetic field would cause an airplane's instrumentation or a ship's navigational system to go haywire. So there's definitely been measurements taken where for some reason an intense magnetic field periodically, well, not periodically, because periodically means on a regular basis, but let's say random. There's been random occurrences of an intense magnetic field in the Bermuda Triangle, which is here's another mystery right here on Earth that we don't know why it's occurring. Remember I said that we believe the core of the Earth is what's generating the magnetic field around the Earth? Well, there must be something else that's generating this intense magnetic field that sometime occurs in the Bermuda Triangle. And what's so interesting, what is it? It's Cuba, Bermuda, and Miami? I don't know, but I know Bermuda's one, Cuba's the other. I forget what the other corner of the triangle is that forms the triangle. Why is it that these intense magnetic fields occur in this one little section? That's interesting. And because of that, you have intense storms that occur in that area. Is it something that the Earth is causing? Is it something else? And that goes with the next question. What about unidentified flying objects, UFOs? Okay, you saw how big outer space is, didn't you? You saw how big it was yesterday. Is it possible that in all this vastness, we're it? Is that possible? Is it possible that we are the only life in the universe? And remember what I said earlier about life not necessarily being what we recognize it as, okay? I think it's impossible myself. I wouldn't want us to be the only, would you? It's pretty lonely. Pretty lonely for us to be it. And you know what? Way back before ships were built, everybody thought that they were it. People in Africa thought they were it. People in Asia thought they were it. People in Australia or the North America continent, they thought they were it. It wasn't until we developed the technology to build ships that could go across the oceans and we discovered that there's other people on Earth. It's the same thing with outer space. We just haven't developed the technology to go out there far enough to meet whoever else is out there. I truly believe that. Space is like a vast ocean that we as yet don't have the ships to get out there. If you think of the Earth as your house, okay, as your house, your front door, and you think of the moon, we've only been from our front door out to the sidewalk in our cosmic neighborhood. That's all the farthest we've been. We haven't been across the street. We haven't been down to the corner. We certainly haven't been around the block. In our cosmic neighborhood, we've only been from our front door a few steps to the sidewalk. That's all we've been. So we've been nowhere. And until we develop the technology to get further and further and further out there, it'll be just like way back when people thought that they were the only ones on Earth until they found out that there's other people because they could travel far enough to meet these other people. I do believe it's that way with outer space. I just cannot believe that in all that vastness that you saw yesterday, that we are the only existence of life. I think that's impossible myself. You know that movie Contact? Has anybody ever seen that movie, Contact? Nobody here? It's about SETI, the search for extraterrestrial intelligence, and the very large array that I showed you yesterday, all the radio telescopes. That's in the movie, but the famous phrase from that movie is, if we're the only ones here, what a waste of space, right? All that out there, and for there to be nobody else out there but us, what a waste of space. Okay, all right, okay. Is weightlessness and massless the same? Actually, that brings me to something that I wanted to mention. The way I spoke yesterday may have confused some people. When I was talking about what your weight would be on another planet or the moon, I used the units of kilogram, which was incorrect. I should have said newtons, right? Right, because weight is a force. Your mass is in kilograms, which never changes. Your mass on Earth is going to be your mass anywhere in the universe, but your weight will change. The only way your mass would change is if you cut off your leg, you remove parts of your body, right? But as long as you stay the same, your mass will always be the same. But your weight depends upon, what is weight? Mass times gravity. Gravity is what changes as you go from planet to planet to planet. Your mass stays the same. So I should have said newtons instead of kilograms. Okay. And another thing that may have been confusing, when I talked about a beam of light splitting up into the 6 colors, I used the word primary, which could be that I should not have used that word. Primary colors, I believe, are red, green, and thank you, blue. And you can combine those colors to make all the other colors. So using the word primary, I should not have used that word. Okay. So again, is weightlessness and massless the same? Are they? No. All right, all right. At least how many people can be in a rocket? Well, the Apollo missions had 3. Space Shuttle has more. The International Space Station has a lot of people. So the number of people, that will change as rockets are improved. And actually another question, yeah, that's, okay, that's good. Oh, and by the way, when I was talking about SETI yesterday and I said how they had flipped the switch in Puerto Rico and in California, you may have wondered, well, what happened after that? Unfortunately, because no intelligence signals were picked up after a long time, the United States government, just like with the shuttle program, saw fit to end the program. You know, government officials, they wanted us to get something immediately, right? And again, it's going to take a while to make contact. I mean, you saw the distances. Even light takes millions of years to travel to some of these places. So we just got to look at the right place at the right time and give it enough time to happen. I do really believe that one day we will contact somebody. But again, keep in mind, we may have already made contact and don't know it. The Mars rover may have rolled over a little rock life form on Mars. Hey, stop rolling over me, okay? So that's not to say we already have not come in contact with life, but it's just life as we don't know it as life. Okay. See, now here's an example of a question that I would want the person to contact me, because it's more of a, okay, apart from studying the space, what is the economic importance of knowing much about the space, applications of space? Remember I talked about that, the batteries that were needed to be developed for Curiosity and Galileo and some of these other space probes. They are of so much benefit to us here on Earth to have that technology. Microwaves come from space. Everything pretty much that cell phones, so many things are a result of space exploration, of the need to be able to go out in space. Can you see the benefit of exploring outer space? It makes us develop technology that is also beneficial here on Earth. That's the big thing. In addition to exploring, and I believe as a human race, our nature is to explore. That's why way back when, people looked out across the ocean and said, I wonder if there's anybody else out there. The human race has never been content to just sit and exist. We've always wanted to know what's around that next hill, what's over that mountain range, what's down in the ocean. That's the same drive that drives us to go out into outer space, that curiosity. And to do that, the technology that we've had to develop winds up being, it's a win-win. You know the phrase win-win? It means you win no matter what. Exploring outer space, not only do you learn more about our amazing world of nature, but you also develop technology that is beneficial to us right here on Earth. That's a big, big plus of space exploration. It helps us right here on Earth. And that's what government officials need to understand. They need to realize, I mean, a lot of them, they don't really know what outer space is. They think it's just something up there that has no use, no importance to us. That's so untrue. Look what we've accomplished, the technology that we've developed for outer space that helps us live right now here on Earth. Okay. Since Pluto is no more, how many? So again, this question about space applications, contact me and I can give you more details, but I think you get the point. I think you get the point of the importance of space applications in space. They're applied right here on Earth. Since Pluto is no more, how many planets presently exist? Well, like I just said, since Pluto's no longer a planet, you might think it might drop from 9 down to 8. No, 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 no. We now think that there's a couple other planets further out that we are just now being able to detect. So, the question is, we actually don't know how many planets are in our solar system. If one wishes to travel to the moon, how can one go about it? Okay, I talked about that yesterday. Here's another one where you contact me. I want to know the career opportunities and benefits of being an astrophysicist. Okay? I became an astrophysicist because I was always interested in outer space. That's what got me in the high school that I went to in Omaha, Nebraska. When I was in high school, a long, long time ago in a galaxy far, far away, the normal routine is that your freshman year of high school, ninth grade, you took a course that's called physical science. And what it mainly was learning about laboratory equipment, Bunsen burners, pH paper. And then your sophomore year, you took biology. And by the way, I just realized the other day that the first Nigerian that I ever met was my biology high school teacher. You know? Yes. His name was Mr. Bangura. I had forgot about that. I was 15 years old at the time, sophomore in high school. We're talking 1971. Mr. Bangura taught me biology. Yes, he did. I still remember. I still remember the way he spoke. It was my first time meeting a Nigerian and the accent, and I just thought that was so cool. Mr. Yes. So, and then junior year, yeah, oh, he was tough. Mr. Bangura, one of the hardest tests I ever had was, it had a full drawing of the human body, and Mr. Bangura wanted to know every single organism or organ in your body. Yeah. I got past it, but whoo, that was a rough one. And then your junior year, you took chemistry. Well, then in my high school, it decided to offer physics for the first time. My senior year of high school, 12th grade. So I took it. Part of it was astronomy. I always knew I wanted to be a scientist because I always, from a little kid, I used to, in my backyard in Omaha, I would dig in the ground, and if I'd find a tree root or something, I would imagine that I'd found a dinosaur bone or something like that. So I always was passionate about the unknown and discovering new things. And so I was always interested in outer space, very interested. So when I took physics as a 12th grader in high school, and I took astronomy for the first time, I found my science. So as a result, when I went to college, I majored in physics. And then in graduate school, I got my master's degree in physics, but with a specialty in space physics and astrophysics, because that's the area of physics that I've always been interested in. So back to that question about career opportunities and benefits of being an astrophysicist. The opportunities are there, which I will be happy to continue the discussion with you via email. And as far as the benefits for me, being able to explore the unknown through research and adding to our accumulated knowledge about the amazing world of nature around us, hey, whatever your passion is, you go for that, whatever it is, because it'll never get boring, you'll never get tired of it. It'd be nice to get paid for doing it, right? But my definition of doing your passion is you would do it for free. You would be so happy doing it that you don't even have to get paid to do it. So an extra blessing is if you get a job in your passion and then you get paid for doing it too. Okay, the concept of dark energy. Remember the slide I showed yesterday, the last slide that showed the Hubble view of all those galaxies out there? And as I said yesterday, you saw how many were in that picture, and that's just a small view that the Hubble took. But imagine the distances between those different galaxies. As I said yesterday, millions and millions and millions of light years. So now it is believed that in all that vastness that I showed you yesterday of what we can see by optical telescopes, gamma ray telescopes, X-ray telescopes, infrared telescopes, all the different eyes that we use to look out into space, radio telescopes were like our ears, seems to be that we've only been able to detect 5% of what really exists in nature. Supposedly, 95% of the universe is made up of what's called dark matter and dark energy. The reason why the word dark is used, that simply means we don't know what it is. We don't know. We don't have a clue. So all that we have been able to detect, which is enormous, as you can see, all those galaxies out there that we can see, only makes up 5% of what really exists. That's mind-boggling. That's mind-boggling. Okay. The possibility of total depletion of the ozone layer. Yes. The effects of aerosols and different things we do here on Earth. You saw that slide about the hole in the ozone layer. And as I talked about yesterday, nature has provided us with protection from the hostile environment of Earth. But now if we continue our practices here on Earth, and eventually the ozone layer is gone, ultraviolet radiation will just come pouring in. And that'd pretty much be it, right? So the governments of the world, they need to listen to the scientists and realize that they need to start putting restrictions on different activities so that the ozone layer can not only not be depleted, but start building it back up again, because we need all the protection we can get from the radiation from outer space. The universe is expanding. Would it stop expanding? See, okay, the expanding, I'm an astrophysicist, but like I said yesterday, the Big Bang Theory, if the universe is expanding, then what's it expanding into? If everything here inside is what exists. And another thing, the Big Bang Theory says that there was this explosion and the universe started from that. It started expanding 13.7 billion years ago. Okay, well, if there was an explosion, who lit the match? Right? Somebody had to light the match. Something had to cause the explosion, which to say that something existed before the universe. Something had to start the universe. So theories like the Big Bang, they're a lot of fun. That's how I look at them. They're a lot of fun, but nobody really knows. Nobody was around and looking and said, oh, there's somebody lighting the match and starting the Big Bang. Nobody was around at the beginning of the universe. We don't know how the universe started. The reason why scientists think that there was a Big Bang is because there's a type of radiation in outer space called microwave background radiation. And it's been around forever. It's very faint, but it's detectable. So scientists believe that this microwave, cosmic microwave background is called CMB. They think that this low-level noise that you can hear with radio telescopes is an indication of how the universe started. This radiation is left over from when the Big Bang occurred. But the bottom line, everybody, is we don't know how our universe started. How could we? We don't know if it's expanding. Well, actually, the reason why scientists, it is expanding because those pictures of the galaxies that I showed yesterday, you can measure the distance, and they are receding from us. Actually, a better model of the expanding universe is to think of, you know what bread pudding is? Anybody ever, you know what? Okay, bread pudding is like it's a dough with raisins in it, embedded in it. So when you cook it, it starts to expand like a cake. So the raisins that are embedded in it, as the bread expands, the raisins, they expand with it, so they start getting further from each other. That's what the universe expansion theory is like. It's a big bread pudding, and the raisins in it are the galaxies, our galaxy, the Andromeda galaxy, all the other galaxies, and as the universe expands, all these galaxies are getting a little bit further and further away from each other, like the raisins in bread pudding. Okay. Okay. Some stars are exploding. Would our star, the sun, explode? If yes, what will happen to the planets? Okay. The sun, I think you remember the slide yesterday where the life evolution of a star, as far as we know, and it's a theory because, again, nobody has been around to watch a star being born, to go through its life cycle, and to come to an end. Nobody has observed that. But again, seeing what's out in space where you see supernova remnants and you see white dwarf stars and neutron stars, and we think we see black holes. But remember, nobody's ever seen a black hole yet. Nope. But anyway, all these different things out there say that, okay, a star can become one of those. The theory is because our sun is what's called a medium-sized star, that the way it's going to evolve is that 1 million years from now, it will explode. And after that supernova explosion, it will either become a white dwarf. Actually, let me rephrase that, because explosion sounds like it's going to break apart. It could explode, but then another possibility, because it's a medium-sized star, it could compress and become a white dwarf. If you have a supersized star, the theory is that a star that big, which is, let's say, 1 million times bigger than our sun, probably the way that's gonna go with it is gonna become a supernova, and then the gases are gonna compress and become either a neutron star or a black hole. But keep in mind, all these are theories. All these are theories, okay? The reason why we think our Milky Way galaxy is a spiral galaxy is based upon what we see that's out there in outer space. We really don't know what our galaxy looks like because we haven't been out there to look back and see what it really looks like. Okay. If rockets are propelled with escape velocity and the velocity regulated to make it orbiting the moon, velocity can neglect, let's see, to do, well, what I said about escape velocity yesterday is it's the same thing with the moon. Just like you need a certain amount of velocity to escape the Earth's gravitational field or to attain orbit, whenever you go to another planet or a moon, because the gravity is going to be different, then you're going to need a different escape velocity, okay? And remember, gravity depends on how big the object is. That's why the gravity on the moon is less than the gravity on Earth, because the moon is smaller. If you have a huge planet like Jupiter, the gravity is going to be much stronger than it is here on Earth. So depending upon the size of the object, the planet or the moon that you're talking about, that will determine the escape velocity. Remember that equation yesterday where mass was in it and the radius? The radius is the distance from the center of the planet to the surface. So the bigger the radius, which means the bigger the planet or the moon, the stronger the force of gravity on it. Okay? If information from the galaxies, you can kind of tell what I'm doing is I'm just kind of doing certain questions that I think I haven't addressed before. if is a form energetic particle the speed for its energy, then why do we not have different light speeds with different energy? Okay. As you saw yesterday, the electromagnetic spectrum consists of a range of energies, okay? Now, energy and speed, there's a direct relationship when you're talking about material objects, solid objects. But photons, remember, which are the particles of light, photons have only one speed, which is the velocity of light, because they are particles of light. And you saw we have, of the electromagnetic spectrum, we have radio waves, microwaves, infrared, optical, ultraviolet, X-ray, and gamma ray. But all of them are photons, okay? You have photons that are part of the radio range. You have photons that are part of the microwave, and so on. They all move at the velocity of light, but they have different energies. Remember how I said yesterday that gamma rays are the most powerful form of energy known to exist in nature? Which is true, but they move at the velocity of light, just like gamma rays are photons. And you have photons that move with energy in the radio range, but they all move at the speed of light. Okay. The sun has its planets, the stars have their planets. Is it possible that some human beings can be in some of the planets which are like in the solar system? Yes, as I said, we just have to get out there far enough to discover that. Yeah, is there any other planets that is habitable? Yeah, I talked about that. I'm sure there are. And once again, they could be inhabited by life that we don't know. How did you get the distance of the Milky Way and galaxies, since there has not been any spacecraft that can travel through space? That's because we use light to measure, like for example, the moon. The time that it takes light to get to the moon, or actually from the moon to us, if you know that time, how long it took, then you can determine the distance, okay? Because if you know the speed of something, like light, and you know how long it took for that to get to you, then you can tell the distance, okay? That's how the distances to those galaxies that I talked about yesterday has been determined. Because we know the speed of light, and as far as we know, the speed of light is the same wherever you go in the universe. Now, we're going on that assumption, but who's to say that if you get far enough out in outer space, maybe the speed of light is different? We don't really know, but as far as we know, the speed of light is constant no matter where you are in the universe. So having that information, that light travels at 298,000 kilometers per second, and knowing how long it took the light to get to us, that tells us how far away these objects are. Now this is an interesting one. I just want to read it. I'm not going to answer it, but it's an interesting question. Is it true that pictures of angelics and heavenly hosts are real? How true is this? Interesting question. Whoever this is, send me an email. All of you, at any time, send me an email. But this person, we can continue this discussion by email. Okay. Okay. What are the benefits? Yeah, I went over this. The importance of exploring space. The planetary bodies, what keeps them in place. Okay, that's the gravity. The force of gravity around from the sun keeps the planets orbiting. You know the centripetal force, right? F is equal to the mass times the velocity squared divided by the radius. Sorry, force is equal to the mass, times the velocity squared divided by the radius. mv squared over r, centripetal acceleration, right? It's like twirling, having a rock on a string, and you're twirling it in a circle. Think of my hand as being the sun, and the rock as being a planet, and the string as being the gravitational pull of the sun on the planet. And I'm twirling it. And if I was to cut that string, the rock would fly off into space. So if all of a sudden, if the gravitational pull of the sun on the earth was broken, for some reason, the earth would just fly off into space on a tangential line to the circular orbit. The solar system is in the outer space. What is holding them? How come they didn't fall since there is no gravitation in space? Woo! There's gravitation everywhere in outer space, okay? There is nowhere in outer space where there's zero gravity. The correct term is microgravity, all right? Gravity exists everywhere. Why? What causes gravity? Tell me somebody, what causes gravity? Mass, that's right. And as you saw, space is full of not only our solar system, but other solar systems, right? There's mass all over space. Yes, the distances are vast, but because there's mass, there's always going to be gravity in outer space. Are there stars that don't explode? Yes. And by the way, when a star explodes, you might, maybe from the movies, you might think that there's fire and you can hear the explosion. No. When a star explodes, there is a big release of energy and a big release of light, but there is no sound because there's no air in space. And actually, you might wonder, what is the difference between sound and light? Well, we all know that sound is much, much slower. Sound needs air to be transmitted. When I talk, my vocal cords causes the air right in front of my mouth to compress. And as that compression, that wave compression travels out, it hits your eardrum and it causes your eardrum to vibrate, and then your ear transmits that vibration to the brain that we interpret as a sound. But in outer space, there is no air to transmit sound. You have to have air to transmit sound. Light doesn't need anything to travel. Light can travel through a vacuum. So that's the difference between light and sound. In outer space, there is light. There is no sound. Another Bermuda Triangle question. I would like to know what causes the bones or muscles problems to those that visited space. Okay, every creature on Earth, humans, animals, plants, we all grew up in the gravitational field of our planet. From the time we're born, we constantly have that 9.8 meters per second squared pulling on us. So as a result, our bones, our muscles, that's what they're used to, okay? So if all of a sudden you're in an environment where it's not 9.8 meters per second squared, it's something else, either less or more. In this case, it's less, right? Astronauts. So your bones and muscles, they're not used to that different acceleration because all your life you've lived in it. It's like having ankle weights on that were put on you from birth, and then all of a sudden when you get to be 15 years old, or better yet, get to be 60 or 80 or 90 years old, and all of a sudden they're taking off. I bet it'll be weird. You're not used to that extra weight. Okay? So, yes, that's why bones and muscles is called atrophic, I think is the term. When astronauts come back from extended time and space, they have to be picked up and carried off of the spacecraft because they can't walk. Because the time that they spent in space, if it's a good little while, their muscles atrophy and they cannot walk. When they have to readjust to the gravity of Earth. Okay, let's see. How is the universe? Will the universe end? Okay. As you saw, supposedly the universe is expanding at 68 kilometers per second, and at this point, it's estimated to be 13.7 billion years old. And my question about what is it expanding into? So, yeah, unless there's some kind of wall out there, out of our existence that, I mean, think of a balloon that's being blown up inside of a room. And so eventually that balloon will get big enough to fill the room and then it'll pop because it can't expand any further. Well, I don't know if there's a wall out there because that would be outside of our universe. So then would it be in existence? See, there's one of those questions that just keep going around and around. What exactly are constellations? Constellations they're groups of stars that a long time ago people looked up and said, wow, that group of stars looks like the shape of a crab. Or that group of stars looks like the shape of a scorpion. Constellations are stars that, because the way they're grouped together looking from the Earth, they look like things we're familiar with. The Greeks believed that their heroes, when they met their end, that the gods rewarded them by placing them in the night sky, like Orion the warrior. You know Orion's belt, the 3 stars, and then you got 2 stars that represent his club, and then I think another star represents, actually he's a hunter, not a warrior, but another star represents his prey. They're simply groups of stars that look like different things that the ancient peoples were familiar with. That's what constellations are. Nature didn't say, okay, I'm going to put these stars together so that they look like a bear or a dipper, a big dipper. No, or a lion, right? No. Just like somebody looks at Orion and sees a hunter, somebody else could look at the same group of stars and say, oh, I see a pot sitting on top of a stove, okay? That's what constellations are. They're just groups of stars that look like different things we're familiar with. How many stars are visible in the night? Hey, there's as many stars in the sky as there are sands on the beach. I mean, it's just unimaginable.
Thanks for letting me go over, Ray.
This is another alien question that I talked about, and we can sure talk about it more. Oh, gravitational wave detected, and how can it be explained? Okay. Yes, I would say about a couple of months ago, there's an experimental group in, I think, Germany that say that they think they have detected gravitational waves. Now, remember yesterday that light has a dual nature. In some cases, it seems to act like a wave. In some cases, it seems to act like particles, which we call photons, particles of light. Well, in the same way, it's believed that gravity has a wave nature and a particle nature. Now, the gravitational particles are called gravitons, and then the wave is called gravitational wave. Until confirmed, we've not been able to detect either. See now, remember I was telling you yesterday about the importance of mathematical equations. Another thing that where if a mathematical equation doesn't correctly describe what we observe, then it's not worth anything. The other side of that is that sometimes mathematical equations can predict certain things about nature before we have the technology to discover that. Good example. Einstein predicted as far back as 1905 in his general and special theories of relativity that the ultimate speed of anything in our universe is the speed of light. And we couldn't prove that until we developed the technology like those accelerators that I showed you, the Fermi Tevatron and the Large Hadron Collider, until we developed machines that were powerful enough to propel protons up to very high speeds where they get to be 0.9 the speed of light, but not 1.0 the speed of light. So from our experiments, it looks like Einstein's theory was correct, that nothing that we know of can travel at the speed of light except light. And certainly there's nothing that can't travel beyond. So the movies with warp speed, where you can go faster than the speed of light, hey, that could very well be possible. Wormholes could be possible. But we don't know because we don't have the technology yet to create such things. But what I wanted to say about Einstein was, part of his special theory of relativity was if something was able to go close to the velocity of light, you have time dilation and you have length contraction. So what that means is that something that can go very close to the speed of light, time for it will slow down according to Einstein. And also, the length will contract. Think of for time dilation, there's what's called the twin paradox. What that says is that if you have two twins that are born, one stays on Earth, one travels in outer space, say for 20 years. Well, when that twin comes back from outer space, that twin will be younger than the twin that stayed on Earth. Because as the twin in space was traveling at high velocities, time for that twin slowed down. So that twin is not as old as the other twin that stayed on Earth. Now, we weren't able to prove, so remember Einstein predicted this, but we weren't able to experimentally prove it until we developed machines like those accelerators. And here is how it was proven. Remember I talked about quarks yesterday, the subatomic particles that are smaller than electrons, neutrons, and protons? Well, there's a quark called a meson, and its lifetime, it's created when two protons hit each other. Its lifetime is like 1,000th of a second. Now, in these particle accelerators, when this meson is moving close to the speed of light, but not exactly at the speed of light, it lives a little bit longer. Instead of only existing for 1,000th of a second, it exists for 2,000th of a second. You see my point? Until we develop machines that could propel protons up to these high energies, and until we had particle detectors that could determine how long this particle existed before it disintegrated, we couldn't detect that small, minute change of this particle existing a little bit longer than it normally would have, okay? That's time dilation. Length contraction, imagine a ruler that's 1 meter long, and if it could travel at close to the speed of light, it would actually get shorter, okay? Length contraction. Again, back to the particle accelerators. The linear accelerator in California, as the name implies, it's linear, it's not circular. So they were able to measure that a fast-moving proton would cover a shorter amount of distance than another proton that's traveling slower. Or actually, the time it took for the proton to get to the other end actually contracted compared to a proton that was not traveling as fast as this proton that's traveling at the speed of light. So the distance for the fast-moving proton actually became shorter than the other one. So again, here you have a theory, a mathematical equation, Einstein's general theory of relativity, E is equal to mc squared, is part of that, which predicted that these two things would occur if an object was able to attain a speed close to the speed of light. But we weren't able to actually experimentally prove that until we developed the technology to do so. So, in a good way, mathematical equations can predict what is possible so that when we do develop the technology, we see that it's proven correctly. The downside of it is that sometimes mathematical equations, see, theoretical physicists sometimes get lost in their equations. Remember I said an equation's not worth anything if it doesn't correctly describe what we observe. So imagine the person who came up with the equation that describes how gravity acts that I talked about yesterday. Okay? So I dropped my pen and it took about a second to fall to the ground. Now, if that equation said that it should take my pen 5 weeks to fall to the ground, then there's something wrong with my equation, right? Because it doesn't describe what we actually see. It takes my pen 1 second to fall. This equation says it should take 5 weeks. That equation is not any good. So sometimes mathematical equations can be misleading in predicting what should happen. Okay, so again, mathematical equation is only valuable if it describes what you perceive with your senses. Sight, hearing, taste, touch. Sight, hearing, smell, taste, and touch. Okay. Okay, that's a similar one. That's a similar one. What is the difference between asteroid and meteorite? Asteroid are the particles. Yeah, some of them are very small, but they're the solid rocks that orbit between the orbits of Mars and Jupiter. A meteorite is a piece of rock that reaches the Earth from outer space. Most of them burn up in the atmosphere before they reach the Earth, but some of them do reach the Earth, and those are called meteorites. Asteroids don't come to Earth. They orbit around the sun between the orbits of Mars and Jupiter. And actually, they do collide sometimes. The asteroid belt has been decreasing as time goes by because every now and then one asteroid will hit another one and send it flying off into space. So the asteroid belt is less populated than it was 1 million years ago, okay? But that's the difference. Asteroids orbit the sun between the orbits of Mars and Jupiter. Meteorites reach the Earth. Let's see. what's the astronaut pin made of? I would be interested to know that myself. I would be interested to know that. It's going to have to be such that whatever substance is used to write is going to be something that's going to adhere to the paper and it won't float up. For example, a pencil. If you were to use a pencil in outer space, you know how a pencil works. You write on something and the small pieces of graphite stay on the paper. And that's what we see as the writing. Well, in outer space, because of the microgravity, remember, not zero gravity, there is gravity. So graphite, if you're in outer space and the gravity is less than here on Earth, those pieces of graphite are going to float up from the paper, which might not be too good because you could breathe it in. It might get into your air system. That's why a pen would be much more preferable to use in outer space than graphite, because ink is much harder to float up from a piece of paper than graphite is. But I would be interested to know exactly how it works. Okay? Is it true that the Earth will soon blow up and people are moving to Mars? They can survive. Because according to what you told us, the quantity of the oxygen in Mars can be sufficient. No, there is not sufficient oxygen on Mars. We would either have to take the oxygen with us, or we would have to be able to grow plants on Mars within a building to produce oxygen that we could breathe. But there is not a sufficient amount of oxygen on Mars that we could just go there and breathe. Now, I'm not even talking about the other hostile conditions on Mars, like temperatures, the gravity, but just in terms of oxygen, nope, we'd have to take it with us, or we'd have to grow plants that could produce oxygen for us. Okay? Oh, and as far as will the Earth blow up? No, not that we know of. Okay? Not that we know of. In order for the Earth to blow up, that would mean that there'd have to be, remember, we don't know what's at the core of the Earth. So whatever is at the core of the Earth, if something was to happen, some type of nuclear reaction or something, that's about the only way the Earth could blow up, and that's not going to happen as far as we know. And as far as people moving to Mars, we've been to the moon, and you remember how I was talking about how in our cosmic neighborhood we've only been from the front door to the sidewalk. That's what I consider the moon, as being from our front door to the sidewalk. Mars, I think of as being across the street. So the big, and hopefully the governments of the world will unite and keep the idea of going to Mars alive, because that would be the logical place for us to go to, would be Mars. Venus is close as well, but the atmosphere of Venus is carbon dioxide. And you know carbon dioxide is very, very lethal. So, and Mars is a solid body. It has an atmosphere, but not as lethal as Venus. And there's all kind of theories that life once existed on Mars. It's very possible. And that's another reason why Mars is so interesting, because maybe Mars was like the Earth millions of years ago. Maybe there was a civilization that existed on Mars. There's a lot of indications that Mars used to be blue. It used to be habitable. We really don't know, but there's indications. There's evidence that rivers once flowed on Mars. There's canals. So it's very possible that Mars was once like Earth, and something happened to cause it to become the way it is now. And you can see the importance of studying Mars, the greenhouse effect that we're so concerned about, the hole in the ozone layer. Who's to say that if we don't do something about that, in 1,000 years, Earth will become another Mars? We'll disappear. The environment will become hostile, unable to support us, and we'll disappear from the universe. Mars could be an example of what could happen to us here on Earth if we don't take the proper steps to protect our planet. It's the only one we got, okay? We can't go nowhere right now. We better take care of our home, right? Yes. Okay. Is it true that a star is bigger than the Earth? Yes. In fact, the picture, you've seen pictures of Jupiter, right? The big red spot. Has everybody seen that? Those pictures of Jupiter with that big red spot. You know that big red spot on Jupiter is a big storm. It's like a big hurricane, and it's about 100 times bigger than the Earth. Yeah. Yeah, Jupiter is a big planet. Jupiter is the biggest. In fact, Jupiter got its name from the Greeks or the Romans. Yeah, the Romans. In Roman mythology, Jupiter was the head god. Okay? Greeks called him Zeus, but he represented the same god, the leader of the gods, Zeus, Jupiter. The reason why that planet was named Jupiter is because it's the biggest planet in our solar system. Biggest one. Saturn is the next biggest. But stars are huge. I think, what is it? It takes about 10 million Earths to make the sun. And by the way, about the sun, it may look like it's on fire, but it's not fire. It's energy, it's fusion. Okay, back to Einstein. With his equation, E is equal to mc squared. E stands for energy, m stands for mass, and c squared is the velocity of light squared. So another prediction that he made back in 1905 that in some cases unfortunately came to be true, his equation, energy is equal to mass times the velocity of light squared. What that basically said was that if I could take my pen, which has a certain mass, and if I could convert that into energy,
I have the same pen right
huge
here.
amount of energy would be released. So what Einstein's equation predicted was that if you could release the energy in an atom, now the mass of an atom is minute, right? You see the power that's released from a nuclear bomb or an atomic bomb? That's what Einstein predicted in his equation, that if you could unlock the energy in an atom, a little bitty atom, look at the amount of energy that's released. And unfortunately, in this case, destructive energy. So imagine how much, if that much energy from a hydrogen bomb or a nuclear bomb is released, imagine the amount of energy that would be released if my pen could be converted into energy. So the downside is the destructive potential of releasing the energy of an atom. But the positive side is if that energy could be harnessed for good. And there's a phrase that says we are all made from stars. You know why that's saying? Does anybody know where that saying comes from? That in all of our bodies, there's pieces of stars. Does anybody know where that comes from? Okay. The reason why the sun burns and all the stars, well, shine is a better word, is because of nuclear fusion. Okay? Now, when you have an atomic bomb, that's nuclear fission, where you break an atom apart. That's how nuclear weapons work. you break an atom apart, and that immense amount of energy is released. But in nuclear fusion, you have hydrogen atoms that are fused together to make helium. Hydrogen is the lightest atom. It's one proton. One proton. So you take two protons and fuse them together, huge amounts of energy are released, just like in nuclear fission where you break an atom apart. So in the middle of the sun, fusion is going on where protons are being fused to make helium, and then these are fused together to make the heavier elements, so you start getting heavier elements like copper, gold, silver, iron, and then when a star explodes, it spews these elements out into the universe, and the theory is that the planets form from these elements that were spewed out in outer space, and they came together to make planets, and we are all made up of the material from our planet Earth. So think about millions and millions of years ago when the Earth was formed. The Earth is made up of elements that come from stars that have exploded millions and millions of years ago. And because we come from the Earth, we have pieces of long, long dead stars inside of us, the elements that are here on Earth. Pretty cool, huh? You can walk around and say, hey, I got stars in me, right? Okay. Okay. I think what is the difference between orbit, telescope, satellite? I think we took care of that one yesterday. Galaxy, planet, and moon. Okay, well, now, a solar system is made up of planets. And remember, we call our solar system because of the sun. Sol, right? S-O-L, that's another word for our sun. The Egyptians called the sun Ra, R-A, Ra, the sun god Ra. You know, I gotta tell you, a very cool myth. See, ancient peoples, they knew a whole lot more than we give them credit for. Remember the Dogon tribe right here in Africa that somehow knew about the binary star system of Sirius long before Western astronomers? These people knew some things that I truly believe we don't even know about. Well, the Greeks had a myth to explain why at dusk and at dawn you see the pinkish red in the sky. What they said was that you had the sun god and you had the moon god. And every day they fought. They had a battle. So in the morning, the two of them are fighting, and the sun god wins and drives the moon god to its cave. And the blood from the battle is the reddish that you see in the sky at dawn. Now the moon god has went away in its cave, and it's getting stronger. It's getting ready to go again. It comes out, they fight again at night, and this time the moon god wins and drives the sun god to its cave. And so the reddish that you see in the evening, that's the blood from that battle. Pretty cool, huh? That's not a bad explanation. So every day and night, they fight, one wins, and then the other one wins. Okay. Why does light travel faster than sound? Remember I said sound depends upon air? Well, light is composed of photons, which don't have a mass. Sound uses the molecules of air. Remember I said about how the sound waves travel? Sound needs air molecules. Air molecules have mass. And having mass, they cannot travel at the speed of light, like photons can. And that's why light travels faster than sound. Okay? See how we're doing on the time here. Oh, got about 5 minutes, okay? Again, you will have my email address. And as I said, contact me anytime and ask me about anything. If I don't know the answer, I will find the answer for you and I will get it to you. Let's see. Did everybody get a chance to see my business card from JPL? Okay, keep it going around. Keep it going around. And my IDs.
Okay, you want them to see his photographs?
Yeah, I just wanted to, that business card, I was so proud when I got that business card. I mean, it was my first ever. I really wish my parents would have, still been around to see me do that. And as you can see in my ID pictures, I might grow my hair back out just to see what it looks like. Probably all gray by now, like my eyebrows and stuff, but the point of me passing those around, it took me a long time to get into JPL, okay? But you gotta keep at it. You gotta keep at it. And actually, do you have the computer hooked up right now to the screen? Is it hooked up? No? Oh, yeah. I didn't even notice. Okay.
Electricity in and out.
So much fun answering your questions. I didn't even know the lights were out. Okay. Okay, well, let me say what I'm going to show you if I get a chance. Back in 1994, I had the opportunity to meet Muhammad Ali in California. And I have pictures here of me and Muhammad Ali. And if I get a chance, I'll show you. And he actually stood up and did that, that look he has? And I gotta tell you, this is my first trip to Africa. And I couldn't have thought of a better way to come here for the first time than to visit your country of Nigeria, and specifically this area of Ondo State. I'm told that your nickname is the Sunshine State because of the weather. Well, from me being here and the smiles that I've seen and the good energy that I've seen from all of you, I think sunshine could also mean your most excellent positive energy and your smiles. Now, what I wanted to say, thank you. What I wanted to say was that in 1974, I was a freshman in college, and you had the Rumble in the Jungle. And I remember all of us listening on the radio to that. And when the announcer announced his victory, we all ran outside, running around the campus going, Ali, 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 right? Yeah. Well, I also remember looking in the magazines and seeing the pictures of Ali running through the villages and the cities and the towns and the streets. And I remember seeing the looks on the faces of the children as they ran with him, looking up at him, smiling, just so happy to be running next to this person. Because he inspired them so much. He inspired everybody. So, as teachers, you have the ability to have that same effect on your students. You can inspire them in the same way. Okay? So remember that. Remember that. You can have such a profound effect on your students that nobody else can. Remember that. Because as I said before, you have the most important job in the world, which is teaching and training our future. Thank you for having me here. And remember, keep in contact with me.
This is wonderful. I'm sure he has attended to all the questions. Are you all satisfied? I believe so. Not yet. Well, the problem we have now is this light going on and off. We will have given room to the space clock to take you through, but we will give you 5-10 minutes. Just walk around, relax. Let's have a 10 minutes break, and then you come back. By that time, there will be light. There are some questions on space applications, isn't it? Some people have questions on applications. We will try to see if we can give you, if it's 30 minutes or 1 hour lecture on that before you leave, if there is time today. So we expect you back. Let's have the 10 minutes recess. Please come back in 10 minutes. Thank you.
And here come the pictures I referred to earlier. Okay. That's full regalia. And this was the day I was getting ready to leave, getting ready to head to the airport. And okay. That's Wumi, Dr. Wumi Alabi, the educator who invited me to Nigeria. This is in the airport when I'm getting ready to catch that flight. That was the big poster outside of the university on the way in to announce the workshop. I was tripping when I saw that going in, right? Huge. Oh, I was seriously tripping. Yep, right outside the campus gate. And that should be it for the video. Okay. All right. Okay, now, first of all, the young man that was in the picture with me, his name was Coyote. I don't remember his last name, Kayode. And he basically took me around. I mean, if I needed to go to the store, what have you. Yeah. I mean, very, very, very cool young man. And to my garb, okay. I was taken, and again, he was my driver. Wumi was with me, but I was taken to a craftsman in the town of Akura that took my body measurements. Right, this is a custom-made garment, and now the hat, I think they might have miscalculated the size of my head. Excuse me. I think they might have undercalculated the size of my head, right? I think it's looking like it's just not quite fitting, isn't it? Like it could be a little bit bigger. But as the colors of this garment and the design definitely are specific to a tribe in Nigeria. So if I was to wear this out and about in Nigeria, people would look at this and they may not think that I was from that tribe. They probably would think, oh, he got it as a gift. But again, it would identify that particular tribe within Costa Rica, the color and the design. How cool is that? Okay, I'm going to end with this. I would only hope that I would get those kind of questions from the Borucas. And I think I will, because they're basic. You heard, you saw. They're basic questions that these
primary and secondary school teachers in Nigeria asked. And I think the same questions would come from the Boruca. And by the way, there is no such thing as a bad question. Whether you're a student or an adult, whoever your teacher is, if you get discouraged from asking questions, don't even let that faze you. Questions are what has brought the human civilization to where it is. That inquest, that inquiry, okay, that always questioning mind. Never, never not ask a question. The worst thing to do is not to ask that question. Ask that question, okay? There's no such thing as a bad question. So I'm looking forward to questions from the Boruca after my presentation. Okay, with that, I will end. Thank you again, Ray, for letting me roll past. Everybody tune in next week. Same fat time, same fat channel.